interview series. Take a load off from your busy workday and listen to the dulcet tunes of our guests, who are all over the cybersecurity landscape. We're going to ask them some hard questions, not going to lie, probably some softballs too. But no matter what, it's going to be a good time. So sit back, pour yourself a nice hot cup of coffee, or something stronger if it's that time of day, and enjoy Coffee Talk with Serge.
Hello and welcome to Coffee Talk with Serge. I'm Audra Streetman, joined today by Eric McGinnis, who is a senior threat researcher here at Splunk. Eric, thanks so much for taking the time to talk.
Yeah, thanks so much for inviting me. Really excited to talk about detection as code today.
Yeah, detection as code is the topic for today, which is something that I'm still learning about. So I'm excited to ask you some questions. But before we get started, I want to talk a little bit about your career and how you got to where you are today, and a little bit about your role, because currently you're on Splunk's threat research team. So tell us a little bit about your career journey up until this point.
Yeah, sure. So I started out really as a software developer. That was kind of my passion that I found in undergrad and then in grad school at the University of Delaware. And I did a number of internships at the Johns Hopkins Applied Physics Lab, where I worked in actually their space department. They launched a lot of spacecraft. And I got to actually work on flight software that ran on a pair of satellites and really enjoyed that. Ultimately accepted a full-time job there in one of their cybersecurity departments and was tasked with a lot of software development. But because it was a small team, we did a lot of our own QA for the tools that we built. So what I found was sometimes you do 5 minutes of development and it would need a couple hours of QA. So a lot of what I stressed was just building better, more robust, kind of automated QA pipelines, because not only does that facilitate faster software development cycles, but it also tends to facilitate better documentation, better history for the performance of a piece of software. And ultimately, that's something that I feel is really important in the security domain as well. It's important to be able to move as fast as, and ideally faster than the threats and the actors that you're trying to protect against.
Yeah, great. And that actually ties a lot into what we're talking about today, because you could say detection as code is very similar to software engineering, but just from a detection engineering point of view, right? Where you're applying some of those same development lifecycle principles and best practices, but in order to improve and scale detections, correct?
Absolutely.
Yeah. So tell us a little
And
bit, for anyone who's not familiar, what exactly is detection as code?
great question. If you look at how the software development lifecycle has changed over the past 10 or 15 or even 20 years, we've largely gone from these really large monolithic releases where they jam a ton of new features, a ton of new bug fixes into a piece of software, and maybe release that quarterly, sometimes yearly, to, if you look at how often your web browser or your operating system might update, sometimes you're getting multiple updates a day, sometimes you're getting multiple updates a week. A lot of those, of course, are bug fixes and new features, but a lot of those are because security issues can spread so quickly nowadays because everything's connected, and not just the good guys, but the bad guys talk when they learn interesting things. So shouldn't we be able to move as quickly from a defensive perspective as both adversaries are able to move and just folks publishing software are able to move? So what we've really worked towards in the space known as detection as code is, instead of just having a search be a search, some SPL, we format it into a descriptive file, and we have a suite of kind of tools and enhancements around it that let you enrich that detection or that search with some documentation, and then actually have an automated pipeline that makes sure ultimately when you bundle that up into an app and run that in your real production environment, it's going to find the things that you intend it to find. And we make that tool chain, that workflow, really easy to use, and something that you can use not only on your own machine to do fast testing and iteration locally, but also something that you can run truly unattended in a CI/CD environment. So we are really trying to take what we've learned from the evolutions in the software development lifecycle and the things that have enabled high quality software to come out sometimes on an hourly basis with updates, and now move that into the SOC so that SOCs can react as quickly as kind of adversaries can.
Absolutely. And that's a big problem right now. You hear time and again about, alert fatigue and just the scale and the speed of attacks ramping up, and the ability to respond effectively and minimize false positives, and a lot of that is through quality detections, and also making sure that those detections are tuned to your environment, right? Because every organization is unique in terms of the threats that they're facing. And I wanted to talk a bit about this from like a SIM perspective as well, like with Splunk, for instance. You talked a little bit about SPL and putting together queries. And for this, when you have, a SIM with lookup tables, data models, you can reuse this code, right? So you have a single piece of logic, but then it can cover events from across your different log sources.
Yeah, absolutely. And so let's drill down for the folks that might not be really familiar with SIM and how useful it is. You might have 3 or 4 or even more different endpoint log providers, and those might run in very different environments. But you'd really like to be able to write a search that works in all of those environments instead of 4 very similar but different searches that work in those different environments. And what SIM's common information model will let you do is normalize all of that raw data into a single common format. And what we've done, which we'll dive into a little bit more detail here, is each of our detections ultimately is powered by a test and a test data set, or even more specifically, potentially, multiple tests with multiple test data sets. So what you can actually do when you write a single detection using the open source tooling that the Splunk Threat Research team publishes is you can say, here are 4 data sets from 4 different environments, 4 different endpoint providers that all should distill down into the same common information model, data model at the end of the day. And you can actually individually get results for, did my search work against these 4 different data sets? So I have confidence that it's going to work not just in one of my environments, but all of the environments that I want to deploy this piece of content or this search into.
And that reminds me of, which comes first, the test or the code, right? Because we hear about like test-driven development where you create a test case and then you develop the code in order to meet that test. What do you think about that? Are you a fan of the test-driven development?
I definitely am. I'll kind of talk a little bit about the life cycle of a detection for our team. We always start with some test data, and sometimes that test data is something that another researcher has published open source on the open internet that's available to us. Sometimes it's test data that's available in, for example, something published by CISA or another kind of respected agency or another AV vendor. Or sometimes it might actually come from an internal Splunk environment that we've seen. But more often than not, there's actually not test data available. So we go out of our way to actually simulate as close as possible in one of a number of simulation environments the attack that we're trying to detect. And very commonly, we'll use another open source tool that our team has published, which is called the Splunk Attack Range, also available on GitHub, like all the tools that I'll talk about today. And we'll simulate that attack. We'll have real data that represents what that attack looks like, and then we'll start to craft our search from that. So it will be my recommendation, if possible, I know it's not always possible, to always try and start with a real data set that's representative of the attack. And then ultimately you can test the content that you're building against it. But I understand that sometimes that's not feasible because not every attack, not every threat has some sort of proof of concept that's available in the wild. So sometimes it really needs to be a best effort. Here's what I think it will look like. But you also need to have some sufficient documentation around that search and around that content. So as new knowledge and information around that threat or around that attack becomes available, you can go back and update your search so that hopefully you can improve the performance or maybe in the future actually associate some test data with that.
Mm-hmm. And you talked a lot about QA, quality assurance, and also some of the other things you did with software development. What are some of the other parallels between detection as code and the software development life cycle?
Yeah, so I think another one of the really strong parallels is some form of documentation, ideally inline documentation. So for the folks that do write searches and other content today, if you're lucky, you might have some documentation that's probably in some third-party system like a wiki or an issue tracking system or emails, post-it notes on someone's desk. More likely than not, that documentation lives in someone's head that hopefully still works at your organization when you need that documentation, and hopefully they have a great memory. What we do to the greatest extent possible is in these descriptive raw data files, in these descriptive files of our detections, which have a bunch of enrichment fields, we actually put a description, so a nice long plain text version of why we've written this search, what we think it's supposed to do, some instructions on how to implement that search. For example, if you might need certain configuration in your environment, you might need certain Splunk TAs or other apps. And then finally, we'll even include a section called false positives and even additional things that I won't go into today, like tags for MITRE tactics and CVEs that might be associated with this. So being able to take all that documentation and put it as close to the actual search as possible in the same file that actual search exists, instead of spreading it all over your organization and all over 15 servers, makes it really, really easy to figure out at a glance, what is this thing supposed to be doing? And more importantly, if it's not doing that thing, what was the person thinking when they built it this way, and why did they build it this way?
Right. Because you can't be a mind reader, right? You got to document, you have to keep it organized, have a consistent method for that. Definitely understand. I'm also curious about metrics, right? Because how do you measure the effectiveness of a detection once you've created that code? How do you test it? How do you measure it across time, especially with continuous integration, making sure that it's continually effective, if not more effective?
Exactly. So there's a number of metrics that we track. Some of them are what you might call softer metrics. Some of them are a little bit harder. Some of the softer metrics are, does every detection that we author have a bunch of fields that I talked about before? So does everything have a meaningful description? Does everything have meaningful how to implement fields? Those are things that we make sure that each detection includes. Those are a little bit softer. And then from a harder perspective, every time we write a detection, actually, not just before we release it to the public, but before we actually approve a pull request or a merge request into our repository, we'll actually set up a Splunk environment fresh with all of a specific set of TAs installed with specific versions. And then we'll actually replay the data that we talked about generating a little earlier into that environment. And we'll execute the search that you wrote. And we will actually make sure that the search hits on the raw events that you expect it to hit on. And if a piece of content doesn't pass one of those tests, not only do we get a nice descriptive output on what failed in our CI/CD pipeline, but we will not merge it in and we will not release it as part of an official enterprise security content update or ESCU release until we've rectified all of those different stages of that test.
Okay, got it. And what about, static analysis of code? Are there ways that you're implementing that? I saw a term called linting somewhere when I was reading about this. Is that something that you're doing as well, like manually going through and testing code that way?
Yeah, exactly. So that is another one of the steps that we do in kind of the validation of our raw content as we build a full version of ESCU that will release to customers. We have a number of quality checks on the SPL itself. One, to make sure that it's actually valid SPL that executes on a search head without throwing errors. And two, we also enforce a number of best practices. So for example, even though this happens all the time, you probably shouldn't be searching by raw index. You shouldn't be searching by raw source types. There's a number of things that are suggestions that our tool will make if you are searching in that manner, so that you can run those queries either more maintainably in your environment or with better performance in your environment. So we definitely do a good amount of kind of static analysis of your queries, and then the tooling helps do the dynamic runtime analysis of those queries as well.
Great. And this is obviously very modular in the sense that you can reuse it. It's cross-functional. And then you mentioned before having a repository to store things like GitHub, for instance. Is that kind of your go-to? I know that's where you have attack range and a bunch of other things. Is that where all of this is stored and held?
It is. All the things I've talked about today, from the actual tools to the actual content, and even the attack data, which is another repository that we use to power all the tests for all of our detections, are truly open source. But we are not just using Git and specifically GitHub to make it open source. The most important part for us is actually the version history that comes along with Git. So we talked about before, we really care about writing and authoring detections that work, that are very well documented. Well, it's pretty common that once a detection is written, it doesn't just stay the way that it's been written for 5 years. It gets changed, it gets updated, and it's important to see who made those updates, when they made those updates, and the explanation for why they made those updates, which you can often see in Git commit messages. And that way, when something changes, if it's not working, you can go back to whoever made the changes, ask for a little bit of information about why they made those changes. And if something was introduced by mistake, it makes it really easy to roll back to a working version, as opposed to having to reverse engineer what the detection was supposed to be doing before a well-intentioned person introduced a defect into it. So again, the version control aspect is not just important so that we can share our work with the community, and also, even more importantly, have input from the community in terms of PRs and issues and other suggestions, but so that we and the community have a history of how the content that we've built has changed and evolved over its life cycle.
hmm And with real world detection use cases, what are some of the biggest challenges or limitations that you've come across with detection as code? I mean, could this be used in any detection scenario, or are there limitations to where you can implement it?
Hmm. I think one of the biggest challenges is uh, everyone's environment is just a little bit different. And our team tends to publish a fairly generic version of a detection. So there may be false positives in specific environments. For example, we have a lot of content around, I'll say, either use or abuse of Windows PowerShell, which of course is very, very commonly used by adversaries because it's on essentially every Windows box out there. And why is it on almost every Windows box out there? Well, because it's a powerful system administration tool that saves system administrators a lot of time. So a lot of our PowerShell content is intentionally broad because we don't know what should be allowed in your specific environment. So what we do to help you tune that is we've pre-populated a number of what we call filter macros on the end of every detection so that you can filter out the results of our slightly broader detection to filter out all those false positives that are specific and unique to your environment so that you still get the useful kind of broader content that we've written. And as you write that filter macro, you're kind of annotating, here's what I know is benign or I'm not worried about in my environment, so that your results are filtered down to the things that you really want to do, really do want to see and really do care about.
Absolutely. So it's not always out of the box, right? Sometimes you have to fine tune and make it work for your own environment, which makes a lot of sense. And that's worth, emphasizing, especially if people are pulling those detections, because it's a great starting point, but it's not always ready to go from the start. I wanted to ask before we wrap up if there are any other projects that you're working on or anything related to detection as code that I didn't ask you that you wanted to include here, especially with, best practices and the whole development life cycle.
Yeah, I think I'll just touch on in order the number of the different repos that our team specifically has in terms of open source projects that you folks might be able to leverage in their own environment. The first one is github.com/splunk/attack range, and that is the environment that we use to simulate all of our attacks. We make use of that environment, which itself makes really wide use of another open source project called Atomic Red Team, which is something I'd really encourage folks to go poke around and take a look at. It's a really powerful tool built by a company called Red Canary. Once we've generated all those uh, test data files, we'll actually upload those to our second repo, which is github.com/splunk/attack data. So we've got at this point hundreds, if not thousands, of categorized data files at that repository. The third repository that we have is github.com/splunk/security content. And that's where we put all of our raw content, which are in those big descriptive YAML files. And then finally, the thing that turns all of that raw content, which is in YAML files, into the Enterprise Security Content Update, or ESCU app, that a lot of folks watching might actually have in their Splunk environments today, is a tool called ContentCTL, which is at github.com/splunk/contentctl. So in fact, for folks that are interested in building content like STRT builds content, that's an open source tool that they can actually use to set up and build and validate and ultimately release content into their own environment using the exact same tooling and the exact same process that the Splunk Threat Research team uses to build quality, maintainable content. So that's something we're really excited to share with the community as well.
Yeah, there's so many resources, and we'll absolutely link to each one of those that you just listed in the notes for this. So thank you for that, and I'll find all those links and add them. Is there anything else you wanted to add, or is that pretty much the gist of detection as code?
I'd say that's pretty much the gist. But to us, the community is really, really important. So whether you have positive or negative, which we like to call constructive, feedback on our content, on our tools, things that we do have, things that we don't have, but you'd like to see us have, or changes that you'd like to us to take a look at, please feel free to reach out directly on our GitHub if you're sharing something in public. Make it an issue, make it a comment, open a PR. Or if it's something that you want to share privately to us, you can always reach us at research@splunk.com. Goes to my whole team. Or if you have a contact, a Splunk contact on either the sales side or the support side, feel free to reach out to them and they'll make sure that ultimately that feedback gets to us as well. We're always really excited to do engagements with either current customers, potential customers, or just folks in the community that are interested in the work that we're interested in. So always really happy to just have a one-on-one or 1-on-15 call with you and your team and talk through some of the tools that we have and some of the challenges that we're facing and some of the challenges that you might have in your environment. So we really love when the community engages with us, Splunk user or not.
Yeah, absolutely. And it's very important that they know that you are there and wanting to engage like that. So that's great. Awesome. Well, thank you so much, Eric, for taking the time to talk. I've learned a lot from this conversation. So thank you again. And thanks everyone for watching.
Yeah, thank you. And hope everyone has a great day.
Yep. We'll see you next Tuesday. Bye.
Bye.